functional domains of eigenmodes of the Laplacian and random functions.
Thank you very much. Is this working? Yeah, can you hear me at the back? Okay. It's a great pleasure and honor to me, for me to be here to talk at this occasion. I met Gelfand many times, especially when he was in New Jersey. I spoke at his seminar a number of times and was put through the experience that many people have described. Always learning as he would interrupt, but I now understand that that was supposed to be a good thing if he interrupted, so I feel quite good about that. The topic I've chosen here is one I've been working on, but also one that he showed great interest in, so I think it's probably appropriate. And in particular, in one of his seminars, he told me that he'd worked on one aspect of what I'm going to discuss here in those early formative years that people spoke when he was very young, when he was thinking about spectra of different things and eventually coming up with Banach algebras. But as you've all heard, any general theory that he would come up with was always based on examples, very concrete examples. And I will concentrate on some such in a minute. Okay, so I'm going to talk about eigenfunctions. Throughout X is a compact n-dimensional Riemannian manifold that's sufficiently rich for anything I want to describe. I was told to make this a colloquium-style talk, so I'll at least spend some time giving you the picture of why many people are interested in this. The Laplacian is just the divergence of the gradient relative to the metric on this compact Riemannian manifold. And we want to study the solutions to the equation Laplacian phi plus lambda phi equal to 0. And these are the eigenfunctions and eigenvalues. There may be multiple eigenvalues, and that in some problems that I'll discuss in a moment could upset things, but hopefully they don't upset any statement we make. So we take any orthonormal basis. All eigenfunctions phi j in this talk are normalized to have L2 norm 1, even if the manifold is not compact, which it may eventually become, because the cases we understand best are the ones which are non-compact in an arithmetic setting. It's an old theorem of Weil, which was probably proved around the time that Gelfand was born. I think Weil shocked everybody by proving this, shocked Hilbert anyway. It's one of his first theorems, and it's sort of the only really general and universal theorem in the subject, and that gives you a count of how many eigenvalues there are on such a manifold. More generally, you could have a Hamiltonian. I'll mention this in a minute. I've written this in an unusual way because I'm going to be looking at the eigenfunctions. I'm not so interested in eigenvalues at all in this talk, other than to have the eigenvalue as telling me the numbering of which mode it is and sort of what frequency it's oscillating at. So this asymptotic law is due to Weil. There are many proofs of it. It's a fundamental fact. The remainder term in this is much discussed. This is not the topic of this talk. I'm interested, as I said, in the behavior of the eigenfunctions as the eigenvalue goes to infinity. So high-frequency eigenfunctions on this compact manifold. In terms of classical mechanics, this Laplacian is the quantization of the motion called the geodesic flow on this manifold. So the manifold does not have a flow in it, but the unit tangent bundle or the unit cotangent bundle has a flow. You take a point and direction that defines a geodesic, that defines a vector, a tangent vector, let's say, and that defines a unique geodesic. You flow arc length t to a new point and direction. And you can do it in the cotangent space. And that happens to be a Hamiltonian flow. And from that point of view, the semi-classical limit, h bar goes to 0, of the quantization of the geodesic flow is this eigenvalue problem. And one is trying to understand the semi-classical limit, which is a very classical problem and very well studied. So I'm sticking to geodesic flow, not to any more general Hamiltonian. Now, if the classical mechanics is completely integrable, then there's a very powerful understanding of what's going on. And this, Gelfand said to me, he thought about very much. and certainly Bohr thought about this, he invented quantum mechanics without having quantum mechanics. He was able to do quantum mechanics classically. And that's because he could only deal with things which were completely integrable, because he found quantization rules directly at the level of the classical orbits, and that required a complete integrability. It was actually Einstein who first pointed out that you can't quantize. He was criticizing Bohr, saying what you're going to do if your classical mechanics is something like the three-body problem, helium, and Bohr couldn't succeed. Of course, later, things were cleared up by Heisenberg and Schrödinger, and quantum mechanics was born. And then this correspondence principle, the semi-classical limit, became a much studied thing, but very difficult in the case that you're not completely integrable. So this talk is about the case that you are chaotic. And what Gelfand said to me was he was very interested in trying to understand what are the quantization rules if the classical mechanics is chaotic or not integrable anyway. And the moral of the story is there aren't any quantization rules. The behavior is completely different. There is no correspondence principle at the level of individual eigenfunctions. There's something else that takes place. And that's what I want to explain to you. And this topic has become known as quantum chaos, the quantization of a classically chaotic system. Now, it is very difficult to study the eigenfunctions in a chaotic system because there are too many periodic orbits and things like that. And the subject has taken off. It's very, very active in the certain physics community, mainly through numerics. That started in about the 1970s when people got PCs. Now people have all sorts of fancy things. But when they first got personal computers, you would maybe, I think, get a grant if you're in physics. You could get your own personal computer, and then you'd have to do something with your computer. And people have code to compute quantizations, very complicated, very simple but chaotic systems, and high-frequency eigenfunctions. And most of the theory is just looking at those things and trying to say something. But proving things analytically is extremely difficult. And I want to emphasize the study of an individual eigenfunction, one at a time. That's what's really difficult in this. There is Michael Berry is one of the sort of founders of this theory of looking at pictures and making very clever suggestions. And he has a beautiful suggestion. Actually, he usually suggests X and not X. And then he's sure that he's right. Because in physics, if you point in the right direction, that's all you're remembered for. You're not punished for the false statements you make. In his suggestion here is that in the chaotic case, so if you have a classically chaotic system and you quantize it, then the eigenfunctions will look like random monochromatic waves. I'm going to define what that is for you in a minute. And that seems to be quite accurate. It's not universally true. Such statements can never be universally true. But in 2 dimensions and with the crudest features of randomness, especially the ones I want to look at, this seems probably to be true universally. The only case in which anything has ever been proved rigorously in this setting is where you add structure which is not physical. That is arithmetic. And this is a topic that I think I once named arithmetic quantum chaos. It's become quite active. And the issues is the tools that allow you to solve the questions, some of these hard questions that I'll show you, come from different sources, not just familiar semi-classical analysis. And so they're very restricted. But these arithmetic cases sort of sit as like solvable chaotic systems for which you can use tools from L functions, periods, to say things. I'm just going to state 1 or 2 theorems because I want to turn to something that's active right now and quite interesting. So let me show you pictures. That's one reason I'm using this kind of technology. As you can see, I can't type, but I can write still. And I have my most important thing I've ever got is called a scanner. So I can write, scan, and then I can do what I'm doing here. All the pictures in this talk are due to Alex Barnett, a student of Heller who's here in Cambridge, Harvard, who has even got a gallery of eigenmodes that you can't get for free. He wants you to pay for them. I stole one, you'll see in a minute. But his student is much more open source. He'll give it to you if you just ask him. And this is a good example. Here's a billiard table, which is an ellipse. The billiard ball in ellipse is the classical mechanics. It is completely integrable. It's an example. And what are those pictures you see there? Those are actually a sequence of 12 highly excited eigenmodes. And they know something about confocal ellipses, as you can see. What you're seeing where it's dark is where the modulus squared of the eigenfunction is big, and where it's light is where it's small. So if you're thinking of quantum mechanically, this is the probability in this state of the distribution of the particle on the configuration space, not the cotangent space, not on the phase space. And as you can see, the eigenfunctions are concentrating in regions bounded by confocal ellipses. So the first thing is to remark, and the earliest reference I know of this is thanks to Gilliman and Melrose, who seem to have dug up that this is due to Boscovich. So I can beat Manjul. He mentioned Gauss, Disquestionius. This is 1500 and something. That if you take a billiard ball in an ellipse, I'm sure this was known to Euclid, by the way, and you play billiards, so your angle of incidence equals angle of reflection, then your trajectory will be tangent to a unique confocal ellipse or hyperbola, a confocal conic, yeah. And that's the second integral. And what you're seeing here is that classically, this is a projection of an invariant torus in the phase space down to this configuration space, and it's bounded by these confocal ellipses. And the eigenfunctions, highly excited eigenfunctions, know everything about it. And that's why Bohr could quantize, and that's a semi-classical limit. Typically, in a completely integrable system, there are quantization rules, which semi-classically are very accurate. And the eigenfunctions follow the behavior.
Can you give us an idea of what I and J are? I mean, the index of the eigenfunctions.
I don't remember. You mean in terms of, yeah? Sorry, I can't. I will give you some eigenvalues. Right, so since in the chaotic case there's no I and J, that's exactly, there's no action angle variables, and there's only lambda, precisely what Gelfand was quite upset about and everybody else. So I will give you the numbers here when it becomes relevant, the actual eigenvalues. So let's take a different domain. This is now a stadium. A stadium, in the billiard in a stadium is not integrable anymore. It's in fact ergodic and not fully chaotic. There are these bouncing ball modes that you see in the stadium there. That's in figure, well, it's the obvious figure where you see singular behavior for the eigenfunction, which is concentrating on this sort of shaded area, but not coming to the sides. That would be a classical trajectory. There's a one-parameter family of billiard balls, that's billiard motions, which are closed. And so not every orbit is complicated, which is never true anyway in a chaotic system. But here you have a one-parameter family of billiards which are showing their head in the eigenfunctions. Now, I call the next thing a Barnett stadium because he's done these numerics. So if you take a stadium which is fully chaotic and doesn't have these bouncing ball modes, then there's no sign at all of any concentration or any remnants of any classically unstable periodic orbits. And we don't see the classical mechanics in the high semi-classical limit. We see something that's not quite random. You see some structure there, but nobody's ever explained that, either conjecturally or anything. All right, so that's that example. And then, of course, the most interesting example by far is the modular group. And I will spend some time on the modular group. This is a hyperbolic triangle, which is a fundamental domain for the ordinary modular group. The classical mechanics in a hyperbolic triangle is chaotic. That's very easy to prove. That's if you have a negatively curved surface, even variable negative curvature, this is due to Hopf. The classical mechanics is ergodic, chaotic. This happens not to be compact, but what I say can be looked at more complicated arithmetic quotients, which are compact. The existence of these square integrable eigenstates here, so in the lectures up till here, these have been put down, and I want to bring them up again. These are the mass forms that have no Galois representation interpretation, almost certainly, in my opinion. But that doesn't mean they're not arithmetically fundamental. In fact, even their existence is completely tied to arithmetic. They're much more subtle. If you degenerate in the moduli space of curves and you look for cusp forms of this type, they disappear. They only seem to exist for arithmetic reasons. Of course, the arithmetic is not about their coefficients being interpreted in terms of some Galois representation, but their L functions are the same as the Riemann zeta function, and they play a very central role in the analytic side of automorphic forms. So if you want to estimate an L function, I mean, after all, once you prove something's modular and you show its L function's good, it's got the right analytic properties, well, why did you do that? Why did Riemann do that in the first place? He didn't just define it for fun. Is you can then actually prove the prime number theorem. That was his point. So similarly here, there are many problems that are classical about primes, about quadratic forms, about representing numbers, Hilbert's 11th problem, which Siegel's mass formula, since it's got such attention in the last few days, does not resolve. Siegel's mass formula tells you how many ways you can represent a number by the genus of the form. It's a sum over the genus, as we learned. But suppose you ask how many ways you can write x squared plus y squared plus 10z squared. Is there a solution to n equals x squared plus y squared plus 10z squared, where the class number is not 1? You can still answer those questions, and the techniques come from these vibrating transcendental mass forms, which are not Hodge type, as Emerton was defining it. So, of course, they play a very important role, and if you ever work with the trace formula, these guys are there, and there's no reason to remove them, and they are one of my most valued things, so I'll never throw them away. And I want to study them, and that's what the so how do they look when the eigenvalue gets very large? So the most success is on the following softest problem, which is a very natural question. Associated to the eigenfunction, let me define a measure, which is just a measure on the manifold X. Now, I'm now back in general, but in a chaotic system. I take phi, everything's real valued. I take phi squared times d volume. That's a probability measure because I always normalize my eigenfunction to have L2 norm 1. So that's a probability measure on X. And you could ask, if lambda gets large, how does that probability measure equidistribute? If you remember the pictures there, in the case of the ellipse, they were concentrating on these regions bounded by confocal ellipse conics. In the case of the stadium, there was this bouncing ball mode. So it's not true that it doesn't seem that every eigenfunction is becoming equidistributed. And it's, in fact, was proved recently by Hassel that those guys, they are in the limit. There are a subsequence of eigenfunctions in the stadium which do not equidistribute, and they correspond to those bouncing ball modes. So not easy to prove by any means. Anyway, that's the measure mu phi. Now, if you're doing dynamics, you don't work on the space, you must work in the phase space. So it's best to lift this measure, it's called a microlocal lift, to the phase space. I think it's usually attributed to Wigner, this construction, or some form of this. I'm now defining a measure on the unit cotangent space. So I take a smooth function, homogeneous of degree 0 in the xi variables, if you want to think of the full tangent space, but I'm just restricting it to the unit cotangent space. And one forms a differential operator, op f, according to the pseudo-differential calculus. You might ask, quantization is not unique in this setting, but in the semi-classical limit, the answers you get here can be shown to be independent of how you choose this. So degree zero. I'm on the unit tangent space, so it's defined by, degree 0, homogeneous at degree 0. And this defines, for each phi, a linear functional in F. It's actually not a positive linear functional, but it's asymptotically positive, so it defines asymptotically a measure. And this measure, nu phi, is obviously a lift of the measure mu phi, and it is a measure on the unit tangent bundle. And the reason this is progress, looks like now I'm asking about the equidistribution of something more complicated. Well, that's certainly a good move if you can answer the more complicated question. But there's one deep thing you learn, and this is a great observation of Schnirelmann, and that is, it uses Egorow's theorem in the propagation of singularities, but it's really a key insight, that any micro-local lift, we're in a compact space, these measures have weak limits, I'll call it a quantum limit. Any limit of the new phis is automatically invariant under the Hamiltonian flow. So you introduced a more complicated measure, but there's something you know about the limits of these measures. They're automatically invariant under the flow. Now, the flow is chaotic, so there's no unique measure invariant. So this doesn't determine the quantum limits, which is the question we want to describe here. But it does give you a flow invariance, which is a big, big plus. I'm going to stick to manifolds which are strictly negatively curved, for which the geodesic flow is fully chaotic. So there's no question of those bouncing ball modes. The basic theorem, the quantum ergodicity theorem, due to Schnirelmann and later Colin de Verdier and Zeldich, is a statement which says that at the quantum level, there's something like the classical ergodicity of this flow. The classical ergodicity would say almost all orbits are equidistributed. This says that almost all eigenfunctions are equidistributed. That is, almost all of those micro-local lifted measures become equidistributed in the unit tangent space. Almost all means this. According to Weil's law, the way I normalize, the eigenvalues come, say, on average every second. So we have the number of eigenvalues up to x for which the statement is false is little o of the total number. So that's what almost all means. And that's a general and theorem which is completely in the ballpark of micro-local analysis, completely natural and a beautiful theorem. But much more seems to be true from all these pictures. And we call that quantum unique ergodicity. That is that every eigenfunction becomes equidistributed and nothing will go bad. Nothing classical will look different. And this seems to be reliable, at least in the arithmetic case, because it's proved. So this was called the quantum unique ergodicity conjecture. Rudnick and I made this conjecture because it became clear that in the arithmetic case, if you assume the Riemann hypothesis, what's that got to do with this? I'll say a word about that. For L functions, then this would follow. So we had no doubt about it.
So does it mean that your pictures you did show would disappear?
No, that just means those measures become evenly distributed. In the stadium, it's not true. It's not a fully chaotic system. And I said Hassel showed that it's not true that you have individual equidistribution. So I want strict negative curvature, fully hyperbolic, uniformly hyperbolic, classical dynamics.
Show for algebra.
They were correct. Yeah.
Were artifacts of small eigenvalues.
No. The measure is fine out for area the thing. So at the top, the volume it's a cusp. That's why it looked. But at the bottom, it was becoming equidistributed. Oh no, everything is borne out very nicely numerically and everything. So there are two major theorems that have been proved in the last 6 years in this, and there are many, many theorems. I just want to mention two. One is the theorem of Nalini and
About mass forms. It is just about regular phase, right?
the conjecture is general. Hang on. The conjecture is general. It's not proved. Now I'm going to tell you one theorem that's known in general, which it doesn't use arithmetic. And that's this theorem of Nalini and Tharaman. It just uses classical dynamics, hyperbolic dynamics, combined with micro-local analysis in a quite novel and deep way, actually. She's able to do something which I'm about to tell you. And that's a general theorem, and it's got a special place because it's not special using no arithmetic. And that is, she shows that any quantum limit, so any weak limit of these measures, in any fully chaotic case, like a negatively curved manifold, any quantum limit has positive entropy. Remember I told you that the limit is invariant under the geodesic flow, and you can compute the Kolmogorov-Sinai entropy. Well, you can't compute it, but it exists. And the remarkable thing is she was able to prove directly, and she wasn't the first to introduce entropy into this question. Lindenstrauss already had. He was forced to do so for a reason I'll give you in a second. But she proves directly using micro-local analysis and some serious hyperbolic dynamics, mixing these two fields non-trivially, that any quantum limit has positive entropy. And that's not proving that they're equidistributed, but it's a step in the right direction. It says that any quantum limit cannot be an unstable periodic orbit, because that's got zero entropy. resolving a long-standing problem of whether in these unstable situations can a eigenfunction concentrate on an unstable periodic orbit. The answer is no. So that's a quite stunning theorem. Hang on. Yeah, for mass forms, it's a theorem. So for mass form, I will assume, because the proofs are arithmetic, we're going to assume you're a Hecker eigenform. Whenever I say the word arithmetic, Hecker eigen is put in there. And Lindenstrauss was able to prove the full conjecture in this situation. And his proof uses measure rigidity. So what I told you is that any weak limit is invariant under the geodesic flow, but there are too many measures invariant under the geodesic flow, and they can be of arbitrary complexity. So there's this remarkable insight of Furstenberg that, say you take rotation on the circle by 2, that's a transformation, or doubling, x goes to 2x. That's a no-soft type thing, very complicated dynamics, many periodic orbits, measures which are invariant of arbitrary complexity. And suppose you do the similar thing with x goes to 3x, and ask for measures which are invariant simultaneously under x goes to 2x and x goes to 3x, then things, he conjectured, rigidify. It's called Furstenberg's conjecture, about two commuting automorphisms. It's not known, but Rudolph proved a remarkable theorem on that if you have positive entropy for one of the transformations and you are invariant under times 2 and times 3, then you're basically Lebesgue measure. And this has been generalized by Einsiedler, Katok, and Lindenstrauss to the semi-simple setting where you have diagonal actions of higher rank. But you might ask, where did the higher rank come here? It came from introducing p-adics into the picture where you use a Hecker eigenfunction. So the measure rigidity theorem of Lindenstrauss, especially beyond Einsiedler and Katok, allowed him to prove this full conjecture, coupled with some more other ideas. It's kind of a miracle. He had to, so the full Furstenberg conjecture is not known because we don't know that if you don't put a condition on the entropy, then it's not resolved. This problem remains seriously open. So what Lindenstrauss was able to do was take, Lindenstrauss and Bergin actually, take the old ideas of Rudnick and myself and directly show that any weak limit has positive entropy. And then he's able to bootstrap with his full force of his measured rigidity. Okay, so that's the kind of theorem, and it's proved in the arithmetic situation, and it's very restricted, but I hope it's clear that the ideas in the proof come from all sorts of sources, and perhaps not the purely mechanical sources that you would like to see, except for Anand-Thurman's theorem. So for the rest of this talk, I want to tell you, now that we know how these soft measures behave, we can look at something much harder, which was always the thing that some of us wanted to look at the minute we saw the first mass form, a picture of a first mass form which appeared from a Cray in about 1989, and I'll show you those pictures in a second. And so for the rest of the talk, I'm going to talk about nodal domains and what we can prove for those. And these are the zero set, so if we have an eigenfunction, or any function for that matter, the zero set, everything's real valued here. The zero set of a function is the place where it vanishes. It's not clear it'll be non-singular. We'll have to worry about that. But if we are going to model this by a random function, that won't be so much of an issue. The zero sets of random functions are going to be non-singular. I'll tell you what random is in a moment. The nodal domains are the complement of the manifold remove the place where the function vanishes. And those are the connected components of the complement. So these are standard notions in eigenfunctions. If you go, I won't show you pictures, but if you look for, I think called the Kaladny, these experiments where people put sand on a drum and then they take the frequency and it increases, the sand starts to settle at the nodal domains. And they're lovely pictures of this. So what do we know about the nodal domain and the nodal set in general? Well, it is one very basic theorem, the very famous theorem of Courant. The book Courant-Hilbert keeps on talking about this theorem because this is Courant. I don't know what Hilbert wrote and what Courant wrote, but it's a beautiful book. Volume 1 I'm talking about. But this theorem is highlighted over and over again, as you'll see. And the theorem is, and this is a global theorem, that the number of nodal domains in any generality, the number of nodal domains, which you should think of as the number of zeros of a function. This is the zero set of this oscillating, like sine nx and cosine nx. The number of nodal domains for the jth eigenmode is at most j. One can improve that constant. It's not sharp, but it's at most j. And that's a global min-max argument, the way you prove it. Arbitrary manifold. Compact, yeah. Right, otherwise, yeah, we have continuous spectrum. You can't. Then there's a beautiful conjecture of, yeah, this nodal domain, when you have this highly oscillating thing by simple variational arguments, will have to start cutting everywhere in the manifold. This is going to get very complicated, and I'm going to show you pictures in a minute. But there's one thing that one expects to have some universal control over, and that's the surface area in codimension 1 on this Riemannian manifold, that is the n-1 dimensional volume of the zero set. And it's supposed to be of size. This less than means bigger than a constant, depending only on the manifold, and less than a constant, depending on the manifold. And this remains a beautiful, unsolved problem, highly beautiful. And it was solved in the real analytic category by Donnelly and Pfefferman by a very nice argument, taking certain scaling limits and eventually proving highly non-trivial theorems about harmonic functions. Things sort of become harmonic in this question. So the volume of the set where we vanish, I'm telling you general facts. These are the only two general facts we know. And in general, the number of nodal domains needn't grow. So let's just keep that in mind. Here's a picture from Courant-Hilbert. It's Stern's 1925 thesis under Courant. That's a flat torus. We were hearing a lot about a flat torus. There's a flat torus, and this is just sine x, sine kx, sine k1x, sine k2y, plus some other frequency like that, where k1 squared plus k2 squared is a number. You write a number in two different ways as the sum of two squares. And there's a constant in front there. And you can make, and what he shows is you can make an eigenfunction on the flat 2 torus with arbitrary large eigenvalue, and they're only two nodal domains. So these sets, whose length I'm telling you are completely controlled, which are becoming dense everywhere, collapse into just like a jigsaw puzzle, just into two sets. So it's not true that the number of nodal domains need grow with the eigenvalue. But in a chaotic system, we expect much different behavior. And that's because in the chaotic system, we expect that it's going to be the same as the random. Okay? So I am now going to spend 10 minutes on the random case. Now, usually when you're working in the theory of numbers, or you're wondering what's true, the real hard thing, say with a Riemann hypothesis or anything like that, the difficulty with counting primes or estimating or Riemannogen or anything of this nature is the thing is behaving as if it's random, but you can't prove it's random. The Riemann hypothesis, if you take summation mu n up to x, is supposed to cancel up to square root x, but mu of n is a Mobius function. That's tautologically the Riemann hypothesis. So the number of prime factors of an integer is random. It's like supposed to be random, but how do you prove such a thing? Usually, if you're making a random model, it's easy. The probability theory is easy enough for me that even I can do it. When it came to something like the zeros of the Riemann zeta function in random matrix theory, well, Katz and I needed it, but it didn't seem to be known in the math community, so we went and learned what Dyson and Gordon were doing many, many years ago, and Meta. It was all there for us to be used. But this is a case where the probabilists have not provided us the answer. So I've been sufficiently interested that I am trying to work this out with probabilists. And I'm going to tell you that there's a remarkable theory here that I'm sure this is the beginnings of. And that's what I want to describe. So let me tell you what a random monochromatic wave is. This is supposed to be what the thing's modeling. Is modeling the chaotic case, though not universally. So I'll stick to my x. It's going to be a random band limited function. My x is as before. It needn't even be chaotic now because I'm going to randomize over windows. So I'm going to take a Gaussian function. So this means I'm going to take, so I had my orthonormal basis. This will not depend on the orthonormal basis. I take summation aj phi jx. And the aj's are mean 0, variance 1. And that defines for me a probability space, finite dimensional probability space, which is a Gaussian There are many ways of describing it. And the only parameter that I have here, I've fixed my manifold X, is this number alpha, which is the band, the width of the window. And the two extremes, alpha equals 0, are going to be very important, as you'll see in a second. And alpha equals 1 is the random monochromatic. But of course, if alpha is 1, you're saying to me, what am I doing there? There's no window. But what that'll mean in semi-classically, this little o can be improved a lot, is I'm summing over lambda minus lambda to a power which is slightly less than 1. I don't want to go too far less than 1. So it's a window where dyadically this is still, all the functions in this are roughly the same energy. That's a monochromatic case. And the question is, what does the random zero set or connected component of such a function look like? And this seems very difficult. So this is a question in pure probability theory. So let me emphasize this. When alpha is 1, this is the monochromatic case, which is the most dear to us, and in fact, the most difficult case of the theory. And when alpha is 0, this is actually very much connected to a random real algebraic variety. Because if alpha is 0, and I took X to be the projective space with a round metric on projective space, the eigenfunctions are polynomials. This is this compact. The only time where you can write eigenfunctions down are for a sphere or a compact symmetric space, and this is one of them. And they're just homogeneous polynomials of some degree. That's what our eigenfunctions are. So they are homogeneous polynomials of some degree. And I'm not in this, when alpha is 0, I'm not restricting. The band just goes up to the degree. So I'm looking at all polynomials of some degree. And I'm putting on some probability measure on the space of all functions of some degree. So here you can forget everything I said. Just take polynomials in n+1 variables with real coefficients and ask, if I take such a polynomial, what does the zero set of it look like? Is there a law? Is there some universal topology for the zero set of such a thing? Now, the model I'm taking is the natural one coming from the Fabini study metric, real Fabini study metric on projective space. And this is very important, because if you took the coefficients to be random, that's a completely different Gaussian, and the behavior is much, much worse. That is the case that most people study, because the theory in one variable, due to Katz and Rice, about the zeros of a random real polynomial, it's sort of, if I give you a polynomial and I say it's random, you're going to tell me, yeah, choose the coefficients at random. But that breaks symmetry. If you choose that, it only has log n zeros. That's Katz's theorem. And that's because all the zeros want to be near 1. And they're only nearby 1 because, think about it. If x is large, or if x is 0, the A0 coefficient will tell you whether you vanish or not. And if x is large, the biggest coefficient will dominate. So it's easy to see that all the actions near 1, and you've broken symmetry. So by taking this inner product on the space of homogeneous polynomials, which is a band limited with alpha equal to 0, you actually, in this one-dimensional model, using Katz's methods, it's very easy to see that you get n over 3 zeros with probability tending to 1. Of course, the maximum is n in one variable. But in several variables, we're asking how many connector components, what's the topology? And that's what the mass form might look like. All right, so there is a massive theory called the Katz-Rice theory, and it allows you to compute integrals, quantities which are integrals of local, anything that you can determine locally, you can compute its expected value, and any statistic. So if you ask how many critical points a random function in this Gaussian has, there's a beautiful formula due to Katz and Rice and its generalizations, which will give you this expected number in very beautiful terms. If you ask what's the expected Euler characteristic of the total set of connector components, since that's an integral of curvature, say in dimension 2, you will get a closed form formula, and people have found these formulae over the years. In dimension 1, the Katz-Rice formula, the zero set is a set of points, so maybe you were a little concerned. But what's very natural from the Katz-Rice formula in higher dimensions is you can compute the expected measure, that volume in the Donnelly-Pfefferman theorem, the expected n-1 dimensional measure can be computed in closed form as a nice integral. And if you're in one dimension, the measure of a finite set of points is the number of points. And that's why the Katz-Rice formula gives you the number of points in one dimension, but it doesn't give you any clue about the topology in two dimensions. The only reason that whatever I'll show you from here on out can be done is some beautiful work of Nazarov and Soden of 3 years ago, which allows you to get around this. So these questions of the number of components and so on are not in the ballpark of the Katz-Rice, but they have shown that you can do something. So these are very powerful techniques that we are using, as you'll see in a minute. Wigman, myself, Gayat, Welschinger, Larario, and Lindbergh have all now been looking at the topologies, and I want to tell you there's a universal answer for the topology of a random hypersurface, completely universal. And that's what the mass form should look like. Anyway, this is what it should look like. Again, Barnett. Actually, I said at the beginning, this is the one thing that's Heller's. You can see it's quite beautiful. It's got somebody shining a light on the side. So you have to pay for this one. I got it from the black market. But it's good enough that it's worth stealing, isn't it? This is a random spherical harmonic. This is alpha equal to 1. It's a random spherical harmonic in that model with degree 40. And that's at 0 set. And you might ask, how many components does it have? Is a universal law. How many, what's the topology of the nodal domains? What's the distribution of the topology? So I think I said what they proved. I should have said what they proved. Here's their main theorem. This is the main achievement of Nazarov and Soden. That for these, and actually quite a bit more general Gaussians, so they're doing something somewhat more general, but in this case, this is what they would be handling. If you take the random 0 set of a band-limited function, then the answer only depends on that number alpha. There's no other number that's in the dimension, such that the number of connected components is asymptotic to, that would be j. So it's some constant. So remember the upper bound of Courant was that the number of nodal domains are most j. They say there's a universal constant depends on alpha so that you'll have a fraction of j connected components with probability 1. Let me explain what that means. So when the lambda goes to infinity, the set, and you choose any guy at random, the measure of the set of polynomials for which this is true will tend to 1. So you don't have to average over anything. You just take a random guy. That's the number of components it's going to have. So there's concentration at the mean. And now I want to look at the topologies by their method. C is positive, the beta is positive. Sorry, what? C is the number of components. The number of connected components is asymptotic. There's a law of the number of connected components depending universally on alpha, not on the original Riemannian metric. I'll interpret it in a second. So that's a picture of that. Now, if alpha is 0, that's a picture up to 80. This is Barnett. The picture up to 80 of a random plane curve. So in Hilbert's 16th problem, you ask, how can you arrange to be a Harnack curve, which is a maximum number of connected components? So in this model, how many connected components does a random curve have with probability tending to 1? According to them, it's got some asymptotic law. But anyway, that's what the thing looks like. Looks a little different. There is some work which is now, I'm convinced, incorrect. So I haven't highlighted it. A conjecture of Bogomolny and Schmidt, which tries to relate these exact asymptotics to percolation theory. But we now, from numerics, see that it's wrong. So there's probably some connection in dimension 2 with some other statistical quantities, but none of that is proved, of course. Anyway, that's a beautiful picture of a random oval. So if you're asked to draw a random oval, a random high-degree plane projective curve with real coefficients, that's what you should draw. It's got a certain number of them. Okay, using these techniques and some other ideas, Wigman and I have actually been able to show that there's a distribution here. So you could ask in dimension, so in the higher dimensions, we haven't understood this properly, mainly because many of these things are harder to do, and also I don't understand the space on which I'm going to be equidistributed. So let's take the two-dimensional case. We have a certain number of ovals. Each oval is just a circle topologically, so there's nothing to talk about how many circles there are. Everybody's a circle. It's just how many components is the only topological question. But if you look at the nodal domains, that's these complements, they are going to be planar domains. That's essentially clear once the frequency is large, except for very few domains. So you may as well assume they're all planar domains, oriented planar domains, and they are determined entirely by their connectivity. So in this Hilbert problem, you could ask how many of these are simply connected, how many of them doubly connected in that picture, how many triply connected. Is there a universal distribution of the connectivity? And the answer is yes, as I'll show you. And if you go up a dimension and you take the zero set of a random homogeneous polynomial in P3, so in P3 taking a surface now, it'll be a two-dimensional real Riemannian manifold. There'll be many connected components. How many of them, and again, have to be oriented. So how many of them are spheres? How many of them are tori? How many of them are pretzels? Is there a universal law for the distribution? Does it only depend on alpha? And the answer is yes. So the two sets in which will be, in the case of surfaces, we know how to classify the topology of surfaces. When I started looking at this in 3 dimensions, we all seem to, we've solved the Poincare conjecture and the geometrization in 3 dimensions. It's apparently a very difficult problem, as I've seen in the literature, to actually say which 3 manifolds embed into R4. Because those are the ones in which we're going to be equidistributing. So you're not going to have an explicit description of the space in which I want this equidistribution. But that doesn't mean you can't prove the equidistribution. It's just not going to be explicit, and there are many other things that are much harder. So we form a measure. So given any random f, I define nu f, which is 1 over the number of components. This is in dimension 2, the number of nodal domains. And then for each nodal domain, I have its connectivity. So I put a delta mass, that's this integer m, and I get a measure on the integers m greater than or equal to 1. And for n equals 3, I have the genus of the surface, and I have a similar measure associated with each f, which is non-singular. And then the theorem is that if there are universal distributions, about which I know very little except what I'm going to tell you here, there's a measure nu alpha and 2, and mu alpha 3, so these measures only depend on this cutoff band alpha, such that these measures with probability 1 tend to that. And the things I know about these measures is that it gives positive mass to, so every possible topology will occur with positive probability. That gives positive mass to everything that can possibly occur. And it's a probability measure. That's actually quite hard to prove, because who's to stop this thing, this measure running out to infinity? So that's, to understand it more, one wants to experiment. And I'll tell you that one of my undergraduates, Maria Nastazescu, a couple of years ago, computed in the random Fabini study. So the question is, if you take a random curve with alpha equal to 0, what the random plane curve, how many nodal domains will it have? It's 4% Harnack. It's got 4% of the maximum number. That's the numerical constant that comes from a Monte Carlo simulation. I'm sure it's very close to the truth. There exists a number there by Soden and Nazarov, which is positive.
And what is likelihood that the curve will be?
Okay, that I can answer. No, that's 0. No. There are a tremendous number of components. Oh, you mean what's the, is it exponentially small? Yeah, I haven't. This is very hard, actually. This is a question of controlling the variance around the mean. And in some cases, when they have exponential control, in other cases, they don't. But in higher dimensions, absolutely nothing. Just the existence.
Conjecture is exponentially small?
I think so. I think for the number of components. I don't want to say about these measures. Hughes, who continued this experiment, computed in the random plane. So this is again new. So if you take a random plane curve and you ask how many components are there how many nodal domains are there which are simply connected, it seems there are 90% of them. Most of the mass is on the simply connected ones, as you saw in the picture. So in higher dimensions, we don't have complete theorems, so I don't state them, but one can formulate and prove partially these things. So I want to end by returning to the interest in this. So now we know what we're expecting to see. This was an excursion into probability just so that we know what to expect. And there seems to be some really interesting probabilistic features of universal topology of a random hypersurface. And I'm sure that you could go to more than hypersurfaces. But I should emphasize that these theorems that are being proved, they are really existential with very little information about what these measures look like. And each statement there, like you charge each configuration, is quite hard, especially to prove. We at least have. The hardest part was to prove in the monochromatic case, which is the case I'm interested in. So now I return back to the upper half plane and to the modular group, or any arithmetic group. And I look at the question there, and this is what it looks like. So this is a picture of Hedgehog, which came long before all of the other ones. This was the first mass form node. Now, when somebody numerically computes a mass form, the first thing they do is give you the zero set. Because that's the natural thing, is to give you not where it's big and small, but where it vanishes, the nodal domain. So it turns out the modular group has a symmetry. It's not a holomorphic symmetry, but it's got a symmetry z goes to minus z bar, which is an isometry of this triangle. And so every nodal domain is either inert or split. So it either splits into two parts. As you can see, the green ones are split, and all the other ones, the pink and the gray, are inert, meaning this reflection takes it back into itself. And you don't see too many green ones, but if this is behaving like the random model and you put in the Soden-Nazarov expected, it's quite close, and it's quite close, by the way, to the conjecture of Bogomolny and Schmidt, which they wrote a specific constant there coming from percolation. But it's clearly not correct anymore. Because when the data was small, it looked good, and when the data was increased, it didn't get better. So it's one of those things where he's guessed the number quite accurately, but not exactly. So that's what it looks like there. And this is no longer random. And this no longer can I use, I'm not taking linear combinations. I can't use probabilistic arguments. I really have to use number theory to try show. So it's going to be quite hard to show this has what the random guy predicts there, given how hard it was to do the random guy. So let me tell you what we can prove. So this uses pretty much all the tools that were developed. But first, let me show you the measure here. So this tree, in this arithmetic case, and Hedgehog produced 3 such guys with high eigenvalue. So somebody asked what the eigenvalue was. 125 squared, but he's sleeping. 125 squared. I promised one number. That's this eigenfunction of Hedgehog. So the eigenvalue is quite big. What that tree is, in each nodal domain, you put a dot, and you connect the dots if the 2 nodal domains contiguous. And you can easily see it's a tree if this is non-singular. And by the way, it seems that the nodal domain of a chaotic system, like a mass form, never crosses itself. It really, in every numerical experiment, is non-singular, but that is not a human problem. You're not going to prove that this is non-singular by any means that I could ever imagine. It's like saying prove the zeros of the Riemann zeta function are simple. You should be satisfied to prove they're on the line and a half, Victor. So let me just assume they're simple. Then you get a tree like this, and you can compute from, you color in that picture, that's why it was colored in, you get 81% are simply connected, 3% doubly connected, and so on. So whether this is close to the universal thing, I don't know. I don't expect, because I think the lambda has to be much bigger here before it will start looking like that for reasons of the symmetry. But one thing is for sure, one thing I don't know is nobody's experimented, and I hope we'll have this soon, as to what that universal distribution is that we're trying to get close. It's just we have the data for this particular eigenfunction. So I can end with a theorem, the only theorem about eigenfunctions in any chaotic system that apparently I know anyway. I have to assume the generalized Riemann hypothesis, which is apples and oranges. It's not directly related to anything here, but it is used critically at some moment. I'll say just 2 words about the proof, because it's connected very much to Akshay's talk yesterday with periods. Anyway, the theorem is that this is the modest theorem. The number of nodal domains goes to infinity, as lambda goes to infinity in any arithmetic situation. the number of nodal domains, increases like at least lambda to the 1/12th. The real truth there should be lambda, constant times lambda. The lower bound we're getting is lambda to 1/12, thanks to the weakness of the tools that we're using. And moreover, the mean connectivity tends to 2. So the mean number of connected components for a mass form nodal domain is 2, which is what it should be, of course, for the random. And how do you prove anything like this? Well, you don't have randomness, and so you use techniques of you take the eigenfunction. So firstly, how do you even create any nodal domain? One of the hardest things here is the nodal domain is a global topological thing. You can't look locally, or at least I don't know how to look locally and decide if something is a globally, what its topology is. Of course, if there's a small loop there, you can. And in the Soden-Nazarov, the proof that the constant is positive is highly dependent on that. In other words, there's a soft part of the theory, which is an ergodic aspect, which proves various limits exist under scaling limits. But the actual hard part is to actually say some probability, which a priori might be 0, is positive. And for that, you actually have to create configurations, many configurations with a desired property. And that's done very cleverly by making a specific eigenfunction, which is very large at a point, and changes sign very quickly so as to actually produce a little loop. So there are many little loops in the random case. But in the arithmetic case, we have no tools like that. So we use a symmetry, and it's like one of these cases where you have a fixed point argument with some involution. The symmetry allows you to topologically relate the number of sign changes of the eigenfunction on the fixed point set of that symmetry, which is a closed curve in this genus 0 modular curve. And then we try to show this eigenfunction when lambda is large changes sign. And for that, we use all sorts of restriction theorems of the eigenfunction to lower dimensional sets, which we prove in this paper. This paper's just appeared. Yeah, I think it's just appeared. The proof uses period formulas. It uses L functions, obviously. Otherwise, why would we be using the Riemann hypothesis at some point? And it uses airy functions mixed with algebraic geometry. I'll stop there. Thank you. I have some references there if anybody wants.
So are there any questions?
Yes. So if you take a smooth projective variety,
Yes.
the puberty is 2D metric.
Yes.
So
remember the real. I'm taking everything is real here. Yeah. Okay.
you can take a complex
Yeah, you can take
projective a real line. Oh.
and you can take the complex fidelity study. You will get a different distribution. But the same theorems can be proved there. But the growth rate will be different. So not really. No. There's something that's simpler in that case. The scaling limit Gaussian field is actually a Gaussian, while here, the most interesting case, the scaling limit field is a function whose Fourier transform is supported on a sphere. And the fact that you can produce every topology, we use actually Ax's theorem, Ax-Shanuel, in function fields to prove the existence of eigenfunctions with a given eigenvalue with any topology using number theory. So it was quite, at some point in this probabilistic argument, we did use some serious transcendence.
The number of components also are.
For the number of components, it's much easier because you can make a barrier using radial functions, which is what they do. But suppose I want to create a topology, a genus 7 surface. So there's a very interesting way to do that. Yeah.
So any further questions?
I think there is one here.
Right in front.
So if I try to calculate the number of connected components looking on the picture, I cannot.
That's what I colored in.
Because there are very narrow necks.
Okay. Yeah, okay. All the programs, so with Nastazescu, all the time of the program is exactly resolving which way those go. And so the numerical code spends most of the time exactly near there to decide whether. That's a very good point. And this might relate to percolation. This is Bogomolny's cheap argument. So what happens is you're asking, suppose they crossed, and I perturbed it a little bit, does it look like this or does it look like that, right? Which way does it resolve?
No, my question was asymptotically, what are the widths of these nets? Are they exponential or power?
I don't know. I don't know. The proofs of the theorems, so probably, no, that's a very hard question. The proofs of these theorems are completely soft. They use, the first thing is you have to show something's local, otherwise you can't do it. So you show that the number of curves which are sort of winding around everywhere is smaller than the number of components, total number of components, so that you eventually get to study something locally. And then you have a Gaussian field at the end, which is the reason for the universality. And on this Gaussian field, you can compute nothing. So the answer is I don't know, because nobody knows how to compute anything for these Gaussian fields except for the number of critical points and things like that. But this, I haven't looked. It's maybe possible to estimate this.
No, it's experimental. Very nice.
Yeah, I know. So I'm showing you, I believe, all the experiments that have been done on this. I'm sure that as people do more, they'll be. All I can tell you is this young lady who was writing an undergraduate thesis, we spent a lot of time, I just said, don't take the degree very high, but make sure you resolve it, which way it goes, because that completely dictates the topology. And I should say that suppose you had something like this, the square, just sine nx times sine my, and suppose that you perturb it a little bit, and that would, in each of these corners, decide to resolve one way or the other. This is Bogomolny's argument. So since we're looking at eigenfunction, the probability should be a half to go this way or that way. And then you have a square, rectangle, percolation model, where you are flipping at each vertex, half and asking how many connected components are there. And amazingly, this is something that Baxter and Temperley and Lieb computed an asymptotics for. And there's an actual number which he was conjecturing is the number for the number of connected components. And it was good to 3 decimal places, but not 4.
Well, if there are no further questions, so what should we do? Make this a 5-minute?
Yeah, let's make 5 minutes.
Okay, good. So we started that at 12. Let's